In this video, we're going to talk about laws of limits that we can use to help us evaluate limits. So here, we are given that the limit as x approaches some value c of the function f of x is L, and the limit as x approaches that same value c of the function g of x equals m. And I want to specify that c, right, this c value that we are approaching, so c, the number L, the number m, and also a number we might refer to k, all of these numbers they belong in the set or are elements of the set of the real number system. Okay, so they all represent real numbers. Our first law that we're going to look at would be the sum or difference law. And what this law says is that the limit of some function as x approaches c. So in this case, we have the limit of f of x plus or minus the function g of x. And the sum law says that we can take this and split this into two limits. So that would be the same as the limit as x approaches c of f of x plus or minus the limit as x approaches c of g of x. So basically we can distribute that limit in a sense across those sums. Limit is an operation. We're trying to determine what the y value is as x gets closer and closer to a number. So, and since we are given in the top that the limit of f of x equals L, and the limit of g of x as we approach c equals m, we can simplify this in this manner. Okay, so we can basically distribute a limit across a sum, like this would be helpful with a polynomial. Our second law is the constant multiple law. And so this can be applied if we have the limit as x approaches c of some value, some constant k, times the function f of x. Well, the constant multiple law says you can pull that constant in front of our limit operation. Okay, so we can pull that out, in a sense, factor it out when you have a constant multiple. So that k would remain, and from up above, we know the limit as x approaches c of f of x is L. So this would just be k times L. Okay, so we have our product rule or product limit law, and that says the limit as x approaches c of the product of functions f of x times g of x. Okay, so if we were multiplying these, well, that could be rewritten as the limit as x approaches c of f of x times the limit as x approaches c of g of x. So the limit of f of x is L, and the limit of g of x is m. So this would end up being L times m. And something I didn't say in that first rule, the limit of a sum is the sum of the limits. The limit of a difference is the difference of the limits. And here we can see the limit of a product is the product of the limits. The limit of a product is the product of each of those limits. And so here we have our quotient rule. The limit of a quotient is the quotient of the limits. And I'll write that out. So if we had the limit as x approaches c of some quotient, say f of x over g of x, well, that would be equal to the limit as x approaches c of f of x divided by the limit as x approaches c of g of x, which would be L divided by m. So the limit of the quotient is the quotient of the limits. Of course, because we have a denominator here in this case, we have to add a little addendum, and we say, all right, well, this works as long as the limit of x approaches c of g of x. That's not allowed to equal 0, and that's just because we know we can't divide by 0. So we have to add that when we're dealing with the quotient. Or we could say, rather, m is not allowed to equal 0. Okay, so as long as the limit in the denominator is not equal to 0, this will work. We have our power rule. The power rule says that the limit as x approaches c of some function raised to a power, potentially k, that's the same as the limit of the function, all of that raised to the power. So in this case, we would get L to the k. And this is very similar to our root law. And we know this is similar to the root law because a root, a square root, a cube root is really just a rational power. So the limit as x approaches c of the kth root of f of x, well, that could be the kth root of the limit as x approaches c of f of x. Okay? And so that would be the same as saying, well, that's the kth root of L. And this works for any situation as long as, you know, if k is even, whatever that limit value is needs to be positive. But if k is odd, we can have a negative value as the radicand under an odd root. But the value under an even root needs to be positive. So let's conceptualize these rules a little bit. Here we are given that the limit as x approaches c of some constant k is going to be equal to the constant, and the limit as x approaches c of x is going to be equal to c. Essentially, we're just taking that c and plugging it in for x. So here, we're going to use limit laws to find the limit. And we're going to say the limit as x approaches c of some polynomial 2x squared minus 3x plus 1. So looking at some of our rules, we're going to write this out. We know the limit of a sum is the sum of the limits. So this represents the same as the limit as x approaches c of 2x squared minus the limit as x approaches c of 3x plus the limit as x approaches c of 1. So I was able to spread that out and say the limit of each term. And a few of these terms have constant multiples in front of them. So this would be the same as saying 2 times the limit as x approaches c of x squared minus 3 times the limit as x approaches c of x plus the limit as x approaches c of 1. So I pulled those two constants, 3 and 2, in front of each of those limits. All right, so one other thing I can apply before evaluating this, I can say that the limit of something raised to a power, right, that is going to be the limit of that value, all of that raised to a power. So this can be rewritten as 2, the limit as x approaches c of x, quantity squared, minus 3 times the limit as x approaches c of x plus the limit as x approaches c of 1. All right, by our rules that we stated up here, the limit of a constant is just going to be equal to the constant, and the limit as x approaches c of x is going to be equal to c. So I'm going to apply that. This would be 2. This limit we said would turn to c, so 2c squared minus 3. This limit would also be c, plus the limit of a constant would be 1. So this is our answer here. And essentially all that is the original polynomial. You'll notice if I take this original polynomial and I plug c in, this is what I get. So my limit, essentially, all I wanted to do was plug that value in, okay? And when we're doing these problems, we don't have to spread this out and separate this completely every time. It's just I want you to make sure you can understand how these limit laws work. So let's look at one other example. We are going to find the limit as x approaches negative 1 of the square root of 4x squared minus 3x. So I'm going to use all of my limit laws here to write this out. So this would be the same. The limit of a square root is the square root of the limit. So I've got the limit as x approaches negative 1 of 4x squared minus 3x. Now I can apply my sum and difference rule as well as my constant multiple rule. So this is the same as 4 times the limit as x goes to negative 1 of x squared minus 3 times the limit as x goes to negative 1 of x. Or I can write that one further step, 4 times the limit as x goes to negative 1 of x, quantity squared, minus 3 times the limit as x goes to negative 1 of x. So as x goes to negative 1 of x, that's going to be negative 1. So this is the square root of 4. This limit value is going to turn into negative 1. The squared will remain minus 3. And then again, the same limit value will be negative 1. And if I look at simplifying this here, negative 1 squared is positive 1, so we have 4. Negative 3 times negative 1 is positive 3. 4 plus 3, this gives us the square root of 7. Okay? So really, what did I do? If I had initially just taken that negative 1 and plugged it into my function, I would say the square root of 4 times negative 1 squared minus 3 times negative 1. That would give me root 7. And you're probably saying, Miss Stein, why do I have to write it out and expand it every time? Why can't I just plug it in? And the answer is you can just plug it in. That is ideally what we want to do. We're just trying to make sure at this point that we understand how these limit laws work, because the problems will become more complex and there will be situations where we need to spread things apart in order to figure them out. So we want to know how to use these laws. But ultimately, when we are presented with a limit problem, we want to try and plug that x value that we are approaching in. And then if we can't, that's where we start to apply manipulation techniques.